My name is Abdul Dakkak, and the title of this presentation, when I submitted it a few months ago, was Computer Science in Mathematica. It's building Parser Generator. It's in Mathematica, but it's actually more towards the computer science in Mathematica. It's more about how to program Mathematica packages, how to go about writing a complicated piece of code. And the motivating example is going to be a parser generator that's completely done in Mathematica. So this talk is about one thing, and that's something that you all have in common, which is when you have a piece of code, it quickly becomes a very complicated project. And so this talk is going to motivate how to manage this complexity by describing this simple parser generator. So complexity arises because either it's a hard problem to solve, and we're not going to deal with that. Another reason is because it's kind of hard to express on a computer. Computers are bits and bytes and all of that, and you just want to say turn left or turn right. You don't want to type in all this crap. The other one is you're not thinking about the problem very well, so you haven't sat down in a room with a pen and paper and just wrote everything out. You just sort of hopped on a keyboard, started typing printf and all of that. So, and you might not have a good foundation or a good tool, so you might be using the wrong tools. You're not, if you have a problem with sort of managing source code, where to put your source code, how to have revisions, then you're probably not using stuff like Git or CVS. You might not be using an IDE like Eclipse or Workbench or Eclipse or Visual Studio. And the other one is you've written all this code, but you really don't understand what you've written. So the code is doing one thing, you have your own logic, but the code has its own different logic. So there are ways to sort of deal with that. So I think that programmers should start by think about the problem away from a computer. A computer is just for typing. The program should be developed somewhere in your head, on a piece of paper, and you should be spending a few hours or a few days trying to think about what you're actually going to write, researching what others have done. So people might have spent a year thinking about this problem versus you only have 8 or 10 hours to think about it. And you can use those for inspiration or techniques. And maybe you could figure out maybe that's not a problem after all. Maybe you find a library, somebody has developed something already, so you just use their code versus develop everything from scratch. Or maybe you can find there's a Mathematica function that already does it. And usually there's 5,000 or 6,000 symbols you bound. I mean, I usually find a lot of stuff that I usually want to do by just searching the help page. I don't know any, I don't know most of the symbols, so that's usually helpful. Okay, so so you can also have not have a good foundation of the tool. So a lot of times when you start a project, you start from the top down. You want to define your problem, but sometimes it's much better to start by having a good foundation, especially if it's a huge project. Having a good debugger, debugging statement, having a logger, having unit tests. Those are very, very important to start developing those from the beginning, and that's how you could manage complexity. So go to the main part of the talk, which is a parser generator. So who knows here what a parser generator is? Okay. So a parser generator, just you give it grammar. So you give it a language grammar, and it's going to find if the string you pass it in is an instance of that grammar. So you essentially give it tokens that could produce different strings and then you're just saying, is my string, could it be possibly generated by those tokens? So one example is, Mathematica, expr, could be just said, it's an identifier followed by some brackets followed by a sequence of exprs. So you probably use them all the time. So regular expressions are example of parser generators. So string match q is actually is doing it's creating a regular expression here and it's trying to match it against this. So this is saying there's 0 or more a's in that string, and it's asking that question. And the answer is yes. So it actually could be represented. So let me import my message there. So it's actually represented by a finite state automaton, where you start at a start node, and then for all a's, if you see an a, then you go to the a node, and then you sort of loop over until you accept in the end node. And the famous examples of these are Lex and Yak. They sort of just pass it in a bunch of rules, and it's going to generate huge C code for you. Hopefully, I mean, you probably use them, you just don't know. But a lot of languages are defined using these. So there, the programming languages are usually, you have your program string, then you're going to use a parser, which is generated by these parser generators, because nobody wants to write. It's kind of tedious and to write these parsers by hand, and you don't get anything. You don't get so much added value from writing by hand versus just defining at the abstract level and let a program generate the code. Then you convert your string into an abstract syntax tree, which is essentially the expr in Mathematica, the AST. Then usually code goes to a low-level representation, which is kind of between the AST and the sort of machine code. And then you optimize on that sort of machine-independent representation, and then you dump machine code, assembly or C. So feel free to stop me at any point, because I realized as I was putting this presentation, it's this is kind of not too many people would follows. So the task is and this is sort of a very early prototype, is how would you define a parser generator in Mathematica? So Mathematica kind of has some nice features, but sometimes you want to write your own sort of language within Mathematica and just parse that, convert that language into Mathematica and execute that. So some examples, would be defining domain-specific languages where you have your own sort of syntax, it's usually helpful. Or you could define a Python parser and then convert that into Mathematica and execute the code in Mathematica. So if you're given a language, you give it some language, and then you generate a finite state machine, and it executes the code and accepts or rejects the string depending on whether it reaches the end node in the state machine.
Most parser generators like to generate the abstract syntax tree at the same time.
Yes.
So it's not just the problem, but it does. Yeah.
Yes. So this actually does that also. So there's also these groupings, and it could call dispatch functions depending on what depending on the rules that you make. Right. So by sort of separating out the problem into different different sections, so I want to define a parser generator. So the first thing is I have to give it a language for the parser generator itself. And then that would have to be represented symbolically in Mathematica, and then I could generate the, so I'm converting the rules for the parser to bytecode that then get optimized and then interpreted in Mathematica. So by sectioning off these properties, I get some kind of really nice features. So the first feature that kind of nice is, I could separate out the virtual machine. So the virtual machine is going to be defined in Mathematica for now, and then it's going to simulate what a computer do. So if there's a branch, if there's an if condition, then it's going to jump to this location, or it's going to jump to another location. It contains like instructions like save environment, jump to action, increment the program counter. It's very, very, very low level. And that's because the chain of instruction can be complicated. So I have this binary expression, which is essentially identifier plus identifier. And this is sort of the assembly instructions that's being generated. So it's going to match any of these characters, and it's going to do a loop. It's going to capture patterns, and depending on the pattern, might call a function defined somewhere else. Thus, it's going to call this function when it reaches a pattern. Going to match spaces. So this code is just generated by going through the symbolic representation. And then the other thing I could do is generate a graph. Just the.
How did you specify that binary expression of your?
So I'll come to that. Okay. So this is the finite state machine. It's just saying, the start node is somewhere, and I can see the end node here. And then you have to find where the start node is, and from there, what the machine is saying is, there is some path from the start node to the end node, given a string. So it's kind of like, if the start node is like way to the left, actually. So you have to go from here to here, based on a string. So. And that's just for very basic binary operator. Okay, so that's kind of fine. So we've defined the virtual machine, abstractly. Now I want to define the language definition, and one of the interesting things is you don't have to define how you're going to parse the input language. You could just define how the symbolic representation of the definition. So by defining the symbolic representation of the definition, I could generate the parser for the parser language. So I could bootstrap the parser generator. So an example of that is, if I, and then with these patterns, I can lower the instructions to some more basic primitives. So for example, 0 or more is the star operator in regular expressions, or ... in Mathematica, or underscore in patterns. That gets translated to this small binary expression, whereas 1 or more, which is the plus, is the same exact code, except there has to be an occurrence of A at the beginning. So I could just say, essentially that means that, 1 or more is, I could reuse the definitions of 0 or more to define 1 or more. And then, optimizations can be done symbolically. For example, so if I have 0 or more followed by 0 or more, then I could just delete this outer 0 or more, because a star is just a regular star. And then the bytecode, can be easily interpreted in Mathematica, or it can be synthesized to C. Now, the synthesis to C is not there, but it's rather trivial. I mean, it would take probably a day to define. And then by separating the different parts of the project, I could debug certain sections. So if I have a problem with the optimizer, I could just call the optimization. So I know there's a bug here because I have not defined VM. But I could pass in parameters to the optimizer and check, is it actually functioning correctly? Is the lowering stage, I can visualize the lowering stage and say, is it actually generating acceptable code? And then in the sort of code generation stage, I can also pass in the sort of lowering instructions and generate machine level code at that level. So that's usually called separation of concerns, and that's a very, very powerful concept because you want independent pieces of your project that interact with each other through a protocol, but don't entirely depend on one. I mean, they don't depend on one another. They could take, as long as they take this, the expected input and produce an output, then you could just chain them together. Okay, so this is the symbolic definition of these primitive operators, and I have you could define it in a string fashion, these symbolic primitives, but I'm not going to show that. So everything in the symbolic, so you have a pattern of A, which means match the string A, or match the set. So set means or is pattern of A, or pattern of if it's a string, then it's a pattern of B or pattern of C. A sequence is they have to follow each other, so A and then B in this example. Range is anything within that range, 0 through 9. Ordered means the ordered choice, so it's going to match A, and if A is not matched, then it's going to match B. Now, that's very different from stuff like Lex and Yak, where it's going to match A or B. This says this is going to match B only if A is not matched. So this is, if you're familiar with parser combinators, this is a parsing expression grammar. It's a slightly more restricted form of a CFG, a context-free grammar. But it actually, by restricting it, it actually makes certain classes of problems harder to manifest. And it's actually as powerful as CFG. So 0 or more, and then 1 or more are the patterns, and then capture name is going to capture the pattern and going to return a rule with that name and the pattern that's being met. So I think that's sort of fairly, it's kind of much better to sort of look at how it actually gets generated. So if I call lower on any of these, and then generate this string. So I call it so it's called parsing expression grammar. I just replace a P with an M. So the pattern A gets compiled to match the character A and then go to the end state. If it stops at any other point, it's never going to go to the end state. And then the same thing if I do the set pattern, set math. I probably need to put in a, but like if I go to look at the how binary expression bin x is generated. So that's this is how.
Can we just take a look at bin x?
Oh, right. Right. So bin x is right. So Maybe you should look at like identifier. That might be easier. So identifier just says, it could be either a dollar sign or a character, uppercase character, lowercase character for the first character, and then it could also include 0 or more characters that also include digits. And everything is inlined. I mean, you could also have calls, so you can define terms and then get linked at a later stage. So that would allow you to have recursion. So if I could say term, a term can equal to a term. If I inline them, then I have an infinite recursion. But if I do a set delayed, then I would get the and then have it a link step to merge the two parsing grammars. So by also using the symbolic representation, I could do some optimizations quite easily. It's just pattern matching and rewriting. For example, that's 0 or more A. So I have a set of rules that simplify the nodes. And then it separates the language parser from its compiler. And that allows me to define the initial grammar using this framework. So this is at the lowering stage, what we do is we could go from the high-level representation, which is these 0 or more or 1 or more, and do some simplification. So for example, 1 or more of a pattern is equivalent to the pattern followed by 0 or more of the same instance. So we do these optimization, and then we generate, so show you that. We generate a machine, a virtual machine, which has stuff like a jump table. It has the certain properties that are included as a association, and that's the string representation of that code. And this is not something you should probably read, but I mean, for small examples, it's easy to read if you know what this code means. But you can easily generate machine. This is very, very close to machine instructions. I mean, these are go-tos and jumps. Right. And the other way to deal with complexity, aside from sort of separating out your project into separate components, is by visualization. So identifier, we saw that. So this is the string representation of an identifier to match an identifier. So it could be any of these characters for the first letter, and then any of these characters, or a digit for the second character. And I could generate a graph from that. And this is sort of how a machine would execute the code. So I go from a start node, I can match the $sign, and if yes, then I go to the second step. If no, then I have to go check the other cases, and eventually I would have to go to the end node over here. So we're going to have a small example. So we're going to define a digit, which is a range from 0 to 9, and going to define an integer, which is 0 or 1 or more of those digits. So it could be. And then we're going to create a grammar in here. That's going to create a virtual machine, and going to pass the string 2321 to it. So if I do that, I get sort of debugging statement that tells me like what the machine is doing, and I get the int. This pattern is 2321. Then I could define a simplified binary operator. Okay, a simplified binary operator by having an int plus or minus another int, and I'm going to have left-hand side rule and the right-hand side, and I want to capture the operator. And I think the printing causes it to slow down, but it also has checking a lot of states, so I get the rules. Now, one thing that the previous case did not handle spaces between operators, so I cannot write 2321 space plus. So this rule would not match. So it would just return an empty string. And so I could define a spacing. This is a bit more complicated because let's say I want also to handle tabs and new line and r /r/t carriage return. Then if I put those in the spacing in the rule, then I can match a space between the operator. So you could, you're actually interpreting a very, complicated state machine. There's a lot of, there's a ton of states in here that you're sort of, checking. You're not going through wrong cases, but you're backtracking a couple of times. So there's a few things that are not working. So capturing is not entirely working. So this is the if state. This is the definition of an if statement. And to capture that, pattern seems to not work. Example, but yeah. So it fails. It does not. It matches, but it does not capture the patterns that I want. For example, I want the conditional statement and then the left-hand side and right-hand side. And then finally, that by using this technique, you could separate each part of your project into separate components, test them separately, and then you could debug each component on its own. And it might not be efficient to do this sort of there's a lot of assumptions that have to be recomputed at each step. But these parser generators don't have to be efficient. They have to just emit efficient code. So that's sort of the trick.